So we start with a lecture on polynomial. There's basically two parts to this lecture. The first would be focusing on long division, factor theorem, and remainder theorem, which should be familiar to most of you. So if you want, you can skip this first part. The second part is on sum of root and products of roots. So that should be maybe less common to previous syllabus before IB. So we'll start with the definition of a polynomial, usually denoted as px for polynomial or just fx, doesn't really matter. A polynomial is anything that can be written in the form of some power of x times some number, right? And then you can have all the power below the highest power until you have x to the power of 1. And then lastly, you could have a term with x to the power of 0, alright, so just a number. But you cannot have any power of x that is negative or fractional, or you also cannot divide any x. Alright, so if you over this by x, this is not a polynomial. And this would be called a polynomial of degree n. The degree is the highest power, and also the number in front of each power is the coefficient. In the topic of function, we focus on polynomials where the coefficients are real numbers. So for now, you would not see any polynomial with a complex number as the coefficients. Technically, there's one occasion in IB that you would see that, but it's not like you need to actually know what would happen, or you actually know any math about a polynomial of complex coefficients. So a discussion on real coefficient should be enough. So the first thing is the fact that we could divide polynomial. Well, obviously you know we can add, subtract, and multiply polynomial. Multiplying will be expanding. So we'll start our discussion with division of polynomial. Again, most of you should have seen this, so I will just maybe do one example. So the idea is this is called the divisor. The thing that you're dividing is called the dividend. Alright, a divisor have two terms, so 1, 2. Therefore, every time it will divide two terms in the dividend. Alright, so 1, 2, which means we'll write the answer on top of the second term. So what you think is x times what will give you exactly this first term. So x times what give you exactly 3x cubed. So that should be 3x squared. And then you actually multiply it. So 3x squared times x is 3x cubed. 3x squared times 2 is 6x squared. Alright. And then we subtract. Alright, 3x squared minus 2x squared, that's gone. That's what we want. And then we have negative 7x squared minus 6x squared. That's like negative 13. Be careful with the sign. And then we will pull the next term down. And then you think the same thing. So what times x will give you negative 13x squared? So the answer should be negative 13x. Negative 13x. So it's negative 13x squared expand, right, minus 26x. So again, you subtract. That gives like 32x plus 4. Then you plus 32x plus 64. And then you subtract again, negative 60. Now we stop the division when the thing after the subtraction has a degree less than the divisor. Alright, so our divisor in this case have power 1, have degree 1. And now we end up having degree 0. Therefore, that's less than the divisor. That's when we stopped. and we call this the remainder. And the answer of division is called the quotient. Okay. And so you have probably seen this before. This is the same long division when you were in, I don't know, primary school. There's also a thing called the division algorithm. Which is true for all division. Alright, the thing that you're trying to divide, so the dividend would equal to the divisor times the quotient plus the remainder. Another way of saying the same thing would be you dividing the divisor on both sides. So you divide them. So you end up having like the dividend over the divisor would equal to the quotient plus the remainder over the divisor. This is also a useful form. You may recognize this as changing a mixed fraction. Changing an improper fraction into a mixed fraction. Right, this quotient would be the integral part, and then with the remaining proper fraction. All right, what that means is I can also write this original thing, this result of the division, as the dividend over the divisor. This would be the same as this. Okay, this process is kind of important, as you will see in probably the next lecture, and also when we learned partial fraction. So I don't want to spend too long on long division, so that should be it. If you are not familiar, like you haven't learned this or do this before, you might go to your textbook to practice a bit. One thing I want to say is if your dividend or divisor doesn't have every single power going down. For example, if your dividend is like x to the power 4 and then x squared, alright, you might find it kind of difficult to do division. The easiest way to solve the problem would be you put a 0. Alright, so like you add a 0x cubed, then the power would line up perfectly. Then you should be able to divide. And obviously the divisor doesn't have to have power 1. It is also common to divide like with a power 2 or any power at all. Right, then since you have 3 terms, you'll be dividing by 3 terms at a time. So this time the first term in the quotient would be x squared, because x squared times x squared is x to the power 4. Plus x, then you minus. Then you have 0 x cubed minus 1 x cubed. That's negative 1 x cubed. And then negative 3. Alright, then you, same thing, pull down 1 term. Then you can go on. Alright, well this time you would stop when the power you get after subtraction becomes power 1. Alright, because power 1 is already lower powered than x squared. Well, actually, maybe I should do this one. So next would be minus x, right? And then minus x squared. And minus x times 1 is minus x. Then you subtract 8x. What is minus 2x squared? So same thing, what times x squared is negative 2x squared, so negative 2 minus 2x minus 2. Then again we subtract 10x plus 6. And so now we get something that is of degree 1, while the divisor is of degree 2. Therefore, that's it. That would be the remainder, because now the degree is less than the divisor, so this would be the remainder. Now, and then if we look back, our first example, we was using x plus 2 to divide this, and we get a remainder of negative 60. Alright, so if we have fx equal to the dividend, and if we for no reason sub in negative 2, right, sub in negative 2 into x, and then we try to calculate what that gives. This is what? Negative 8, negative 24, minus 28, minus 12, plus 4. Alright, what's that? My mental math is quite bad, so to make sure. Oh, we get negative 60. Okay, what's negative 60? Well, the remainder. And this is obviously not a coincidence. This is known as the remainder theorem. Alright, when you have a polynomial divided by x plus 2, you can get the remainder by substituting in negative 2. Alright, so this is remainder theorem. When fx is divided by x plus a number, then f minus a is the remainder. Okay, now the proof is actually not difficult. All you do is division algorithm, right? Remember, this is basically saying that the dividend, which in this case is fx, the divisor is x plus a, right? Fx would equal to the divisor times the quotient. Well, we don't know what the quotient is, so we'll write it as qx. The quotient is another polynomial, right? Plus the remainder. Now the key is, again, the remainder have a degree less than the divisor, but our divisor already have degree 1, so in order to be less than that, the remainder has to be a number, a constant. So we denote that as r instead of rx, because the remainder now should not have any x, just a number. Alright. Then if we substitute in negative a into x, well, if we substitute to the left-hand side, you substitute to the right-hand side as well, right? We'll have negative a plus a times q of the negative a plus r. So again, r is just a number that does not depend on a, so no matter what you does not depend on x, so no matter what you sub into x, r is just r. And minus a plus a is 0. 0 times anything is 0. So turn out f minus a would give you the remainder. That's why we have the remainder theorem. Well, another version would be, what if instead of your thing divided by x plus 2, it is divided by like 3x minus 1? Well, the answer is you get the remainder by substituting f 1 over 3, by substituting 1 over 3 into the function. The reason being, if the divisor is ax plus b, alright, then in the proof, we will change the divisor into ax plus b. And the key is we want to sub in something that would make this 0, right? So you have to think, what do I sub in into x so that I can make the divisor 0? Then the answer should be obvious, negative b over a, because a times negative b over a plus b would be 0. So that's, we'll change this part as well. Then we'll get the similar result. Then the next immediate result we can get would be the factor theorem, which says if we sub in some number, say fa, into f, and somehow you get 0, then x minus a is a factor of fx. Well, factor by definition means when you divide fx is a factor of fx. If you divide fx by x plus a, you would not get any remainder. Well, the reason why should be obvious, because fa would give you the remainder, but according to remainder theorem, the remainder would be 0, so simply by definition, x minus a is a factor. So let's show you an example of how do we use a factor theorem. We can, for example, fully factorize 2x cubed plus 5x squared minus 4x minus 3. Alright, so factor theorem, the most useful thing is it'll give us a way to factorize a cubic or even a quadratic, a power 4. Alright, you probably know how to factorize a quadratic. Factorizing cubic is a little bit less easy. One way would be using factor theorem, okay, which says if you somehow plug a number into the polynomial, and if you happen to get 0, then you get yourself a factor. Alright, so that's exactly what we'll do. We'll randomly plug numbers into x and hope we get 0. Well, that doesn't sound like a very good strategy, right? Well, turn out that's actually what we do. Except it's not completely random. Turns out, due to like some quite obvious reason, the number that you try to sub in will have to be factor of the last constant term. Okay, so for this case, our constant term is 3, and obviously 3 only have factor 1 or 3. And we also count both negative and positive. That means we will only try plus minus 1 or plus minus 3. Any other number would have no chance. Alright, and it's actually a theorem that if we try all of these and none of them work, then that would mean you actually cannot factorize this quadratic, this cubic, if you restrict yourself with integers factor. So usually what we do is you don't have to tell the examiner the numbers that fails. You only like try one by one and get the one that work, and then you only write down the one that work. It should be obvious that 1 would work, so we'll say like f1 equal this. So for the one that work, you want to show that it really works. Alright, so it's 2 plus 5 minus 4 minus 3. Okay, that's really 0. Therefore, x minus 1 is a factor. Once you get the first factor, you can get the other factor by either doing long division Alright, if you do long division, assuming you did it correctly, you should have no remainder. Alright, at the end it should be nothing. Then the original polynomial would be x minus 1 times the quotient. Therefore, 2x cubed plus 5x squared minus 4x minus 3 would equals to x minus 1 times that quotient. Another way that I kind of like would be you just guess the other factor. Alright, so let me show you once how you guess, see if you like that method or not. Now we know originally this is cubic, while I have a linear factor. What that means is the other factor have to be quadratic. Right, so it would have x squared, it will probably have x, and then we'll probably have a number at the end. It shouldn't be too hard to guess the coefficient of x squared, because no matter what that number is, you need to multiply to the x term to create the x to the power of 3 terms. That means there's no choice but to have a 2 here, right? Because that's the only way you can have 2x cubed. On the other hand, the last constant term have to be multiplied to this -1 to get this last constant term. So it should also be obvious that that's a +3. That's the only way to get -3 at the end. Now, and then to get the middle number, I usually like to use the x squared term. So you think like, how can you get some x squared term? The answer is you can have the constant times the x squared, or the x terms times this x term. Alright, so from the -1 times 2x squared, I would have -2x squared. But at the end, I need 5x squared. Well, that would mean I need an additional of 7x squared. That must mean this is a 7, right? So that when this x times this 7x, you give me that extra 7x squared that I need, so that when I add to the -2x squared, I get what I want. To make sure my guess is correct, I usually check with the x term. So now you think, how can you expand the right-hand side to get some x term? So it should be the number times x and the x times number. So -1 times 7 is -7. X times 3 is 3x. So that does add up to -4. So I know my guess is correct. If you want, you can try the long division. You should get the same thing. Lastly, you would try to see if you can factorize this quadratic as well, which I think this time is possible. And that's a fully factorized cubic. And you probably notice one of the factor have like a number in front of x. It is because the number that you guess in a factor theorem could also be a fraction. So the idea is, have you guessed a -1/2? Alright, if you substitute -1/2 into this polynomial, you would also get 0. And if you sub in -1/2, then the factor is 2x plus 1. Alright, so let's change the theorem a little bit. If you tried a fraction b of a, then the factor is ax minus b. Alright, then you might be wondering, do we just try any denominator? The answer is also no. Turn out, if the number that you have to try is a fraction, then the numerator have to be a factor of the last number, while the denominator have to be a factor of the starting coefficient. So in this case, factor of 3 is only ±1 or ±3, while factor of 2 is only 2 or 1. If you over 1, that's like nothing. So turn out you would, all the possibility would have only been ±1/2 and ±3/2. And again, it's a theorem that if you try all these 4, including this 4, so try all this 8, then this cubic would have no rational roots. And that would really means you really can't factorize it. Okay, so that would be the first part of this lecture. The second part concerns, we call them the relation of roots and coefficients. But we like to call it sum of roots, product of roots. We start with a quadratic equation, ax squared plus bx plus c equal to 0. As you can see, as you probably know, quadratic equation have 2 roots. So we'll call the roots alpha and beta. Now we'll think the quadratic would always have two roots because we'll be including repeated roots. So if this quadratic of two equal root, we'll say both alpha and beta is that same number. And we're also including complex roots. You don't have to actually know anything about complex roots. You can sort of just accept that there is a way to make sure a quadratic equation have two roots. The way to do it is to use something called I, the imaginary number. And like I actually never would show up while we're doing this topic. On the other hand, if you are very uncomfortable with the idea, you can go to my complex number lecture first, which I believe is free on Udemy. But we'll be assuming that a quadratic always have two roots, which is true, okay? And we call them alpha and beta. Now then what happens is if alpha and beta are roots of this polynomial, which would mean if I substitute it into x, I'll get 0, right? That's the meaning of a root. That would mean x minus alpha has to be a factor, and x minus beta also have to be a factor. Now, but if I just expand this, when I expand out x squared, the coefficient of x squared would always be 1, right? But I said I started my equation with coefficient a. So how do I compensate that? The answer is you multiply a in front, okay? Then it must be true that these two polynomial or these two equations are the same, all right? Because they have the same degree and have the same roots. What I mean is, if I expand this, with the a, if I expand this, all right, let's expand it back first. So we have x times x, this, and this, and then this. Then we expand a. Wow, look at this, a alpha x. They all look kind of similar, right? So I have to be careful. Now here we factor out the negatives. These two are negatives. We factor out. Both have a, we also factor it out. Both have x, we also factor it out, but put it at the back. And so middle we have beta plus alpha. We'll write as alpha plus beta, which is obviously the same. This. As I said, this should be the same as the original equation. What that means is we can compare the coefficient. Alright, so we have the coefficient of x, which is b on top, must be the same as the coefficient of x here. So we have b equals to minus a times alpha plus beta, and c equals to this. So c equals to a alpha beta. And so the conclusion is alpha plus beta is, we divide the negative a, so negative b over a. Alpha plus beta, and alpha times beta is c over a. This one is known as the sum of roots because you add them up, and this is the product of roots. And then let me show you a little bit what you can do with this. So usually it's like given some quadratic equation, and then we call the roots alpha and beta. Then they can ask you to find stuff. So the obvious thing to find would be alpha plus beta, alpha times beta, right? Alpha plus beta would be negative b over a, so it's negative 7 over 2, so 7 over 2. Alpha times beta would be c over a, so it's like 3 over 2. But then you can also find stuff like 1 over alpha plus 1 over beta. The reason is if we get a common denominator of alpha beta, then we have beta plus alpha on top. But beta plus alpha is the same as alpha plus beta, so that's 7 over 2 over 3 over 2. So that's 7 over 3. show you one more. Maybe you can look for alpha squared plus beta squared. Then usually we'll use the fact that alpha squared plus beta squared is actually alpha plus beta squared. Okay, you probably know that's not true. Well, actually alpha plus beta squared is alpha squared plus 2 alpha beta plus beta squared. Therefore, alpha squared plus beta squared is actually alpha plus beta squared minus, you minus this away, 2 alpha beta. So minus 2 alpha beta. And so alpha plus beta is 7 over 2, squared minus 2. Alpha beta is 3 over 2. Then you just calculate that. That should be this, I think. Another type of question could be they give you a quadratic with roots alpha and beta. They can ask you to find another quadratic equation. So find an equation that would have roots, maybe 1 over alpha and 1 over beta. Then you can also use sum of root product of root to do this. The way is you assume the equation to be like x minus 1 over alpha times x minus 1 over beta. Right. So as I showed you before, there should be an a, but since this is up to us, a could be anything. So you could like take a to be 1. Right. To make it an equation, you make it equal to 0. And then you just expand this. So it's x minus x over beta minus x over alpha plus 1 over alpha beta, or x squared. Then we have what? Minus 1 over alpha, 1 over beta, x plus 1 over alpha beta. Okay, this should be the equation. Well, but oh, this is a plus, by the way. But by coincidence, we actually have found 1 over alpha plus 1 over beta. That's 7 over 3. So that's 7 over 3. And 1 over alpha beta is 3 over 2. So that's 1 over 3 over 2. Okay, so you can see how they are related. So an equation that would have 1 over alpha, 1 over beta as roots would be this. And then we usually would multiply both sides by 3 just to make things nice. This would be a quadratic that have roots 1 over alpha, 1 over beta. Alright. You can kind of look at the original question and the answer and sort of see how they are related. Right? The next natural progression of this would be going from quadratic to a cubic. So let's say you have a cubic equation, ax cubed plus bx squared plus cx plus d equal to 0. Cubic in general, if you include repeated roots and complex roots, have 3 roots. We'll call them alpha, beta, and gamma. And then the proof of the following is actually similar. You make the factor and then you keep expanding and then you compare the coefficient with a in front. Then you get what I'll show you. It's actually a good practice to do this proof a little bit. As a matter of fact, it has shown up maybe twice in past papers, so it's kind of worth doing just as practice. So it turns out the sum of root alpha plus beta plus gamma is negative b of a. So it's the same as before. And the product of root alpha times beta times gamma is the last constant term over a. However, the trick is the sign, the plus minus, is actually alternating. Whenever it's b is negative, then the next one is positive. Then now at d is negative. So this is negative. If you actually do the proof, you'll see why. Okay, now this is actually what the syllabus says you should know. On the other hand, it's very natural to ask, wait, what about C then? And it's actually so natural that even past people have used the result of C twice in past papers. And since it's not in the syllabus, so the way they test you is they will first ask you to prove this with again the expanding thing that I mentioned. Okay, so you should really try it, and if you really try it, you will see that C over A is when you have each time two of them multiplied together, and then you add up all the possibility that you can multiply two of them. Okay, and that would be C over A. Alright, it's positive because the negative is alternating. B is negative, C is positive, and then D is negative. So you would probably guess that we can go quadratic, part 4. In part 4, we assume the roots to be alpha, beta, gamma, delta, usually. And so similarly, the sum of roots is negative b over a. The product of roots, if you multiply all of them together, is the last number over a, so it's e over a. But again, it's negative, positive, negative, positive again. So e this time is positive. But c, okay, just in case it will come up, c is when you have two of them multiplied and added up. Right, so it could be alpha, beta, alpha, gamma, alpha, delta, plus beta, gamma, plus beta, delta, and gamma, delta. That's c over a. And d would be you multiply three of them at a time and then add them up. So alpha, beta, delta, plus. That's negative d over a. And very lastly, in general, if you have a polynomial power n, so a n x to the power of n, a n minus 1, n x minus 1, plus blah blah blah, until you have a1 x to the power of 1 plus a number equal to 0. Alright, then it's like the b becomes a n minus 1 because, you know, if n is bigger than 26, then we'll run out of alphabets. If you have a polynomial power n, then in general it should have n roots. We call them alpha 1, alpha 2, so on and so forth, up to alpha n. Then the sum of root. So you can write add, right? You can keep adding. Or you can use the summation sign, where I run from 1 to n, alpha I. Is again negative b over a, but b is really a n minus 1 over a is a n. In this case, the product of roots, which is you multiply them together. Product is actually denoted by capital pi. Right, so it's a same kind of logic as summation sign, but this means multiplied alpha I. Then similarly, it is the last coefficient, the constant term, over a. So it's a0 over an. The only complication is, as we've seen, the signs should alternate. Right, the first one must be negative, the next one must be positive, so on and so forth. Well, but then how do I know what's the power of this last one? Well, but then you can also look at the fact that if the power is 4, the product of root is positive, but if the power is 3, the product of root is negative, which means this should be negative if the starting power is even, but if it's negative if the starting power is odd. What I mean is we can just put in front negative 1 to the power of n, because if n is odd, negative 1 to the power of odd is negative, but negative 1 to the power of even is even. Now, I believe in this general case of power n, they would not test you on the middle case, because they will actually need you to prove it, but then the proof will be very difficult to write out because of, like, you have to write in terms of n. So I believe in general they would probably not ask you on the middle cases. So usually in past paper, when they want you to use these, it's most likely straightforward, but we'll demonstrate some of them in the next lecture.